Welcome to this video where we continue to talk about content contained in the book Introduction to Nonlinear Control. And in particular in this video we'll briefly talk about content contained in Chapter 4, Frequency Domain Analysis. While we will be predominantly focusing on system representations and results in the time domain, it is good to have a basic fundamental knowledge on system as in the frequency domain as well. And that's why we are going to briefly talk about some terminology used in the frequency domain, where you then can find details either in Chapter 4 here or in other books. Okay, we start with system in the time domain, linear system, for simplicity, single input, single output, meaning we have two equations here, x dot is equal to ax plus bu, and then an output, y of t is equal to cx plus du. X can be n-dimensional, but the output y is one-dimensional and the input u is one-dimensional. And what we are interested in is now a representation in the frequency domain where S now corresponds to the frequency instead of a time signal here. And we are looking for an input-output representation, meaning if we are taking an input signal in the frequency domain, then the output is given simply by the multiplication with the so-called transfer function. So question is, if we have a linear system in time domain, how do we get the corresponding representation in the frequency domain? So how does G of S look like? Okay, and to get there, we need to first look at the Laplace transform. So a bit of terminology and assumptions. So this, at this stage, unknown function g is called the transfer function, taking complex values here and then returning complex values. We assume here in the context of this talk and also in the book that g is a rational function of the parameter s, and rational function then means it can be represented through a polynomial in the numerator here and a polynomial in the denominator. And we assume that both p and q are of minimal degrees, which means we don't have common zeros here. What is usually done when considering systems in the frequency domain is to assume that the initial condition is equal to 0. So we will focus here on x of 0 being equal to 0. Okay, and with that, now we to see how how to construct this function g of s here. We first need to introduce Laplace transform. So for a function from positive numbers here, so taking arguments essentially with respect to time, we consider this integral here from 0 to infinity, but this here is s where our frequency pops up, so the complex number. And when this integral here is finite, based on this integral, we define the Laplace transform. So for a function psi and for an arbitrary complex number, we denote phi hat of s as Laplace transform of the function psi, defined through this integral. That's maybe an abstract definition, and we don't have to learn it. We can look up the corresponding expression whenever we need it, and the rules that come with it are more important. But before we look at the corresponding rules, just one additional definition, namely the inverse Laplace transform. So the Laplace transform shows us how to go how to start with a signal in the time domain and then return a signal in the frequency domain. If we want to go the other way, then we can take a signal in the frequency domain and return a signal in the time domain. Okay. As I said, the actual definition here is not that important. What is important for the context of this lecture here and in the context of the book is that there are certain properties that come with the Laplace transform. So if we take a couple of signals or functions in the time domain, and if we take three constants in R, then the Laplace transform satisfies these rules here. A couple of them are highlighted, and these are the ones we are going to use here. First one is if we first apply the Laplace transform to a signal in the time domain, and then afterwards apply the inverse Laplace transform, well, then we are back at our original function. So that is kind of a well-definedness property here as the first result. A second property here is linearity. So if we have a signal in the time domain defined as a1 phi 1 plus a2 phi 2, and we apply the Laplace transform to this expression, then this is simply the multiplication of the constant times the Laplace transform of the first signal plus a constant time the Laplace transform of the second signal. If we have a signal phi here and we take the kth derivative of that signal and then apply the Laplace transform, that's simply taking s to the power k times the Laplace transform of the original signal plus conditions on the initial condition. So here, as I said, we are going to use x of 0 is equal to 0 in general, meaning this component is usually not present. Well, and if we are looking at the integral, then we simply get 1 over s, so the inverse of the derivative. Okay. So now let's have a look at our linear system here again, and let's see how to construct this transfer function g for this particular linear system. Okay, so if we start with x dot equal to ax plus bu, y is equal to cx plus du, then applying the Laplace transform here, since we have this linearity property, we can apply the Laplace transform to the individual components, meaning applying the Laplace transform to x dot, as shown on the previous slide, simply means multiplying x with s, and we get this initial condition, but we will set that to 0. And the other signals essentially stay the same. We have a constant times signal, simply becomes constant time signal in the frequency domain. And that we can also do with the output equation, and that is the corresponding equation to the system in the time domain here. From here, how do we continue now to define the transfer function g? Well, we can rearrange the terms. So under the assumption that x of 0 is equal to 0, we can rearrange terms, and we end up with the expression s times the identity matrix minus a times x hat of s is equal to bu hat of s. So that's simply rearranging the first equation and assuming x of 0 is equal to 0. under the assumption that this matrix is invertible, we obtain Si minus A to the power minus 1 multiplied with Bu of S. And then if we plug that in to our output equation here, then we obtain Y hat of S is equal to C times S I minus A to the power minus 1 times Bu hat of S plus du of S. We can slightly rewrite that to Y hat of S is equal to C S I minus A to the power minus 1. B plus D and then U hat of S, which means we recover here our input signal and our output signal, which means we have here found our function G of S as our transfer function, depending here on the parameter S, and the rest is constant. All right, so having that briefly summarized here, so simply by rearranging the terms, we end up with this expression here as derived by hand, which means we can define our transfer function in this particular way. And that in particular means that, yeah, if we have a system here, single input, single output system, we have A, B, C, and D given, then it is straightforward to calculate the corresponding transfer function. Yeah. So that's one important piece, being able to, of this chapter, being able to go from continuous time to the frequency domain representation. A different question that could be asked would be, well, can we also go from the transfer function to the linear system representation? And yes, there are also ways to calculate that. It's not as straightforward by hand, but there are tools like MATLAB which can easily do that. Switching between transfer function representation and ABCD representation. And the corresponding theory can be found under realization theory in the literature, giving this connection between frequency domain and time domain. Yeah, and also these rules, you find them in various textbooks or online, and there are a lot more depending on which properties you need. Because if you go a bit further and look at delay systems or systems with delays and not just linear systems, you might need additional rules here to go from time domain to frequency domain. But all of that can be looked up whenever you need it, and then can be applied in the correct context. Okay, when the representations in the frequency domain important, or how do they help us? So one application would be to look at interconnected systems. There, the representation in the frequency domain is usually quite helpful, and making it easy to analyze these interconnections. So, for example, if we have two systems here, where we then have an input U1, corresponding transfer function leading to an output, and we assume we have this cascade interconnection where the output of one system is the input to the next system, then it is straightforward to calculate now the system dynamics from U1 to the output Y2 simply by multiplying the two transfer functions. The only thing to keep in mind here, which is not important for single input, single output systems, but in the context of multi-input, multi-output systems, the order here plays a role. And of course also the dimensions need to match here. So the multiplication is G2 times G1 and not G1 times G2. Other interconnections can also be looked at, for example, feedback interconnections, and then one can look at stability properties as well, and corresponding controller designs. So a standard diagram would be this feedback interconnection here, where we have our input U in the frequency domain, our output Y, and now we use feedback here again for single input, single output systems, where K is just a real number. We feed the output back with a new input signal or reference signal, and then the overall system dynamics going from an open loop representation from U to Y goes to a closed loop representation from V to Y with this very specific closed loop transfer function, where now the question, for example, could be how to deselect K such that we have asymptotic stability, or in the context of frequency domain analysis, bounded input, bounded output properties. Specific tools that are used in this context then, and which are briefly described in the book, are then, for example, the Bode diagram, which allows an analysis of stability properties, and the Nyquist diagram and Nyquist criterion, which help to answer questions of robust stability, instability, robustness margins in terms of systems represented in the frequency domain. And this concludes this video here, where in the next video I will briefly talk about discrete time systems. So far we've done everything in in continuous time, and then I will briefly highlight that most of the concepts can be also stated in discrete time, but there are a couple of subtleties to pay attention to.